All right, what'd you get for, what would you say that the shape of the distribution is, Alexis? Why don't you share how would you describe it?
I would say that it's approximately normally distributed.
What if we don't know what that means? Can you use other words?
It looks like a bell.
Okay. All right. Anyone else want to add their words? It's okay. You like that?
Yeah, they like that.
They like that? All right, it's all good. What's the standard deviation? What'd you find, Cassie?
6.8.
Do you agree?
I like that.
Leo?
Yeah.
And what was the mean?
Wait.
What was the mean?
30.69.
I was going to ask Leo, but that's okay. Did you get that too? What did you say?
I got what she.
What was it again? 3 point.
Wait, for which one?
The mean. Sorry, the mean. What did you say?
I clicked it, it looked like random calling. Wait, 10.69.
Do you know why I'm not random calling today? It would be like a lot of misses. So, Sebastian, help us out with the next one then. If you take the mean and subtract and then add the standard deviation, what two numbers do we get there?
6.189 and 14.552.
Agreed?
Oh, yes, yes. No. Wait, 6.6. 6.82, yeah. 78.
You're going to pretty big there.
Well, it's 6.
It doesn't matter like a great deal because I think the answer to the next one is going to be the same regardless. It's 6 and change and 14 and change, right? They're close. So what's the number of scores that lie between 6 point whatever and 14 point whatever? Zoe, did you calculate that? How many of the scores?
I'm working on it.
There are 213 total. How many lie between 6 and 14? 6, greater than 6, so it was 6 point something, right? So it has to be greater than 6 point something. And it has to be less than 14 point whatever. 195? So it is. And what did you add up? Which numbers here did you add up? How many, which ones did you add up? 8? This one? This one?
And 14.
Good, but you're adding up the frequencies, right?
Yeah.
Yeah. And you got 195?
No, why don't you?
I think that's right. You want to add up the 31, the 49, the 38, and the 28. So it's 146.
Okay.
Yeah. So good spirit of your solution, but yeah, 146 I think is what it comes out to be. Good. Did you have a question? I don't know anything about normal distributions or empirical.
Isn't it like that if it's within one standard deviation of the mean, that like there's like 16 and then.
If it's normal or something?
Yeah.
Okay. Yeah.
Like, I
Maybe.
don't know if that makes sense. Does that work?
What is the percentage of the? We don't have any assumption here about normality. What is though the percentage that you got? Do you want to share? 146 out of 213. What does that amount to be? Matt. Well, what are you doing down there?
I just put what I thought of as there. Alright, it's 68.5%.
No, it's not.
Oh my god.
Really close, but what was it? It's like 68.
68.5.
Is it exactly 68.5?
Like,
I rounded to near
So yeah, that's good. That's okay. I thought it came out to be a little different. I forgot what it was. That's good. So it is very close to some rule that maybe someone knows, maybe, perhaps. But that's okay. I mean, it does have this like kind of mound shape and stuff. Yeah, we'll discuss it in a minute. Yeah.
So when you were adding the numbers, why didn't you add for frequencies for 6?
Well, because 6 doesn't lie in between these two numbers, whatever you calculate.
Oh, right.
6 is not between 6 point whatever. 14 point whatever. 14 does lie in between 6 point whatever and 14 whatever. All right, so we are going to talk about normal distribution today. Before we launch into that, is there any question that you might still have from the homework from Tuesday, the homework 2 on class data? In particular, setting up your cumulative frequency distribution. And by the way, that was, I don't know if we used the word, it was on the slide, but we didn't say it. Ivy likes to call those the cumulative frequency diagram that you drew an ogive is how you pronounce it. But O-G-I-V-E, ogive is how it's supposed to be. Yeah.
So for estimate the median, you want R&D,
Yeah.
you just like looking.
So you're using a horizontal line to come across and then drop down, right?
But
Yeah.
horizontal line, you're just like, that's a roughly.
I mean, it's a little rough, but I mean, you're actually making a calculation. If you had, I don't know how many pieces of data on the one you had there. What was it? 60. So if you're looking for a Q1 or something, you're going to go to 25% of 60, which is 15, right? And then go across with horizontal line. You might even want to use like a ruler or something, draw it nicely, and then draw down. It's a drawing task to some extent, though, right? And then draw down and see what data that is. And we'll all disagree a little bit. You're right. Yeah. But don't just be like, well, don't just completely give up then and be like, well, no one will ever know and be anywhere even close to the answer. Try still the best you can using that technique. Good. All right. Well, let's talk about the normal distribution a little bit, and our AP stat people can contribute along the way. Those who can help us out with some of these ideas. So you probably, even if you haven't taken AP stat, you probably have had some prior exposure to the normal distribution. So maybe you already have a feeling for what this looks like, and maybe even what kinds of random variables have this distribution. The first thing we should say is that it's a continuous distribution. That is, it's a function of a continuous random variable. It gives the probability density function. Remember, we use the word probability mass function when we're dealing with discrete distributions in our probability unit. Inside of our probability unit, we didn't deal at all with any continuous random variables. But you know that we've made that distinction in this unit. We've been talking about discrete versus continuous random variables. Measures that you could find the length of a phone call. We notice that we never asked any of those questions inside the probability unit. So really, this marks the very first day that, at least in this class, that we considered a continuous random variable and its distribution function. So it looks like this, as you probably, like I said, even if you're not taking AP Stat, probably know. You've seen this shape, the normal distribution, sometimes also called like, Alexis, did you use the word bell curve? Right, I don't know, like some people call it a bell shape. You might also hear it called the Gaussian distribution, named for Carl Friedrich Gauss. And the properties, there are three properties I want to highlight in terms of like identifying a normal distribution by its picture. One would be that it's symmetric. What else do we require? Huh? Yeah, it's certainly true that for any probability function that the area underneath of it is 1. That's true, yeah. What else do you want to say about its shape? Symmetry is not enough, is I guess what I want to say. I mean, you can think of something that isn't a normal distribution, but is symmetric. Why is that not normal? You need more criteria and more demands, yeah. Yeah, okay, so unimodal or single peaked, I think I have written down here. All right, so this is not a normal distribution. So let's try and draw another example of something that's unimodal and symmetric. And then now you need more criteria in your life. Like none of these are normal. These are all non-examples. It needs to be shaped like a bell. Maybe we can use function language to describe the extra requirement we have. I'd like to draw your attention to 2 points on the curve, here and here, where you don't need any statistics lens for this. I just want you to bring a function lens from your algebra 2 experience, maybe even. It's not an idea we've talked about a lot this year, but what are those? You know what those are called on the graph?
Points of inflection.
Does that ring a bell? Yeah. Points of inflection, where the graph changes its concavity from being concave up to concave down, and then over here to concave up again. Does that ring a bell? So we'll pick up that discussion more in like a calculus context next year. But if you were like surfing this function, your surfboard would be below the water over here. In between here and here, it would be above the water if this was like a big wave or something here. And down here, over here again, it would be below the water. You see that? So, bell-shaped is a fine way to say it too, though. Okay, but it does have these 2 points of inflection. The parameters we keep carrying about in this unit and in the last unit, the mean and standard deviation, if you know those two things for a normally distributed random variable, then you know uniquely its distribution. You know exactly which bell-shaped curve we're talking about. And a lot of times, because that's true, that it can be determined uniquely up to those 2 parameters, we often write this, I shouldn't say often, in this class not probably very often, but it's certainly true when you're in the context of a stat class or someday you might take like a probability theory course or something like that. and you have lots of random variables in your life that are distributed among in lots of different distributions, then a lot of times we just write like, oh, has the normal distribution with mean this and standard deviation that. And we use the little tilde to signify that the random variable x has that distribution. If the mean is 0 and the standard deviation is 1, then we have a very particular normal distribution, which we call the standard normal distribution. And the density function is given by, well, I should quiz anyone in AP Stat. Maybe you know it off the top of your head if you're in AP Stat. You know that x equals what? Do you know how to get this curve? No, you're just saying if you wanted to graph this on your calculator, what would you, what function? What's the rule? F of x equals what? This goes to show that AP Stat is not like a full-fledged math class, maybe. Here's a function that you use all year in your class and you don't know the rule. Here it is. If you ever need it, it is painted in red above the lockers right there too. If you need it. That's the normal distribution of it. You don't need to know it. You don't. It does, like it says on this slide. You don't have to know this. But just looking at the equation, you know, one perspective we can bring to the table as a math class rather than in your stat class is we can actually ask some function questions about this. For example, is the symmetry exhibited by this equation? Talk to me about symmetry with that function. What do you see? Does it exhibit the kind of symmetry you think it should be claimed it should have? Yeah, so what does that mean for the function? What kind of function is it? It's even, right? Isn't it? Can you prove it algebraically, right? If you plug in a negative and a positive number, do they give you the same answer, clearly? It's a messy answer, but it will be the same thing. How about the tails? Let's verify. If you plug in like 1,000,000, what that is to say, what's the limit of this function as x tends towards infinity? What do you get if you plug like 1,000,000 in for x? Yeah, you'll get like e to the negative 1,000,000 times a constant out front. Yeah, you get something really small. And furthermore, if you plug in like negative 1,000,000, what's the limit as x is going towards negative infinity? What happens when you plug in negative infinity? You're also getting something small. You kind of get like this exponential decay behavior, but on both sides because of the x squared, right? So I hope you see kind of where this is coming from, why we have this look to the graph. Now, it's still a huge mystery, and you're like, why there's like an e and a pi popping up in this? That is, for now, a great mystery for us. And we won't explain any more of that. And you'll never need to know that function again. Unfortunately, in stat, you don't. But it's interesting to look at least, and analyze. Theoretically, you know, that function would be all you need if you're even in stat class, if you want. You could just use that function. That function is coded up in your calculator under certain commands too. But, changes in mu and sigma result in the expected things we typically would see in any other distribution where we change the mean and standard deviation, right? The mean, of course, changing the mean in this green dashed one, for example, changing the mean does a translation on the data. Changing the standard deviation, or in this case, on the diagram here, it's the variance that they're giving here, right, sigma squared. But changing that gives a change in the spread of the data. But in all cases, like Fatma already pointed out today, in all cases, we have a curve that has under it an area of 1, right? And in red, the solid red line, that's the standard normal distribution with mean 0 and standard deviation 1. And then all the others are various modifications of that. I think I stole that from Wikipedia. Here's my source. Large standard deviation, more spread, small standard deviation, tighter spread. Comments? Along the way. It's also worth mentioning what kinds of things we might see in the real world, so to speak, that have a distribution that's normal. So here are a couple examples, but really we maybe want to think too, like what is the hallmark of being normally distributed? What makes something normally distributed? So we'll turn our attention to that. that question as well. So a lot of tests are like kind of normed according to a normal distribution of some kind. I think the IQ test is 10. This is 100 is the mean, I think, with 100, with 15 is the standard deviation, something like that. So these kinds of things are all almost certainly normal, like data on those things. And then as your stat, I guess in your stat class you've recently even thought about the central limit theorem. One other thing that makes this distribution special in particular is not just that it models certain things, but that it also like undergirds basically like all of our, well not all of, but a great deal of our statistics theory. Turns out that when you take samples, repeated samples from any distribution at all, regardless of how it looks, and you like take the mean of those every time, then that distribution approaches the normal distribution. So we find that to be true. Sums of stuff, if you repeatedly sample anything and then add them up, or if you repeatedly sample things and average them, those always have the normal distribution when you collect lots and lots of observations. So that's really the big idea. And also it somewhat serves to explain why some of these would be normal. I think sometimes we just are like, well, if it looks normal, then maybe it is normal, right? But apply the same level of scrutiny you have with other functions, right, in your life. For example, let's think about an exponential function. If you were to graph a population and it looked exponential, you might be like, well, maybe it's exponential. But that's not really, doesn't really satisfy the mathematical soul, does it? I mean, isn't there a theoretical reason why it should be exponential that maybe you would expect before ever even looking at data? And what for exponential is that? Do you remember what that hallmark of exponential growth is? Like, why is it that even before I look at the growth of the bank account over time, that I should know that that's exponential? Do you remember what kind of the defining property is of something being exponential growth? Well, that's the look of it. But before I ever see data, I already know that. Well, okay. I mean, but I don't know the equation. Maybe I just like have a situation. Maybe you've never thought about it. I don't know. I think we talked about it in our exponential growth curriculum, but the hallmark of exponential growth would be that the rate that something grows is proportional to its current size. Yeah, exactly. And so you can see that if the population is bigger, then that makes for faster growth, right? That's the hallmark of exponential growth, right? If you have a bigger bank account, it grows faster. As soon as you say that, I haven't even seen the data. I don't even know the numbers of your bank account, but I know it's exponential growth because you just told me that the rate of change of the population is proportional to the population size, right? Done. Exponential growth. So what is it for normal distribution? Like, is it, besides actually looking at the data, is there a way to know? And in some ways, it goes back to what I was just kind of discussing here. It really has to do with like a sum of independent processes. And that's the reason a lot of times biological populations, the characteristics of biological populations exhibit that. So what is the length of the cockroach a function of? Well, it's probably the sum of a lot of independent events that have happened, different phases in its maturation. And those together as a sum of independently things serve to be a normal, something normal. Each one being a sum of that thing. But it is a sticky issue, and it's still true that we should look at the data, probably, for the most part. Like, sometimes our intuitions fail us about that. Anyway, take a KP stat for more on that. We'll tell you in this class, for the most part, when something is normal, and we'll allow you to do that. So someone has already maybe used this word today as you engaged in the warm-up, for those who know the empirical rule. It did seem like in the warm-up today, we didn't really know much about the data, but just from the look of it, it did seem to have this kind of property, didn't it? And looking at data and then saying, hey, this looks normal, as a scientist, I would probably call that like an empirical observation, right? I'd be like, hey, I looked at the data and it seems to be normal. That's the process of empiricism, isn't it? So if you have some data and it seems to obey this type of distribution, then we are safe, I think, in guessing that data is probably coming from a normal distribution. Now, already, I want you to notice how these are phrased. I think you understand the first one, right? Because that's what we did in the warm-up. We talked about one standard deviation away, and that's how much data was there. 68.2% of the data was there, or in our case, 68.5% of the data was there within one standard deviation of the mean. But notice here, as we move to the next ones, we're almost starting to use standard deviations as almost like a measuring rod, right? Of like how weird a piece of data is. On average, a piece of data, well, on average, a piece of data is like one standard deviation away from the mean. But if you're 2 standard deviations away from the mean, you're weird, right? And if you're 3 standard deviations away from the mean, you're really weird. In fact, if you live somewhere outside of 3 standard deviations from away from the mean, you live in a very, very, very limited place, right? Almost all the data is within 3 standard deviations of the mean on a normally distributed variable, right? Very little falls outside of that. So I don't know, if you said you were 5 standard deviations from the mean on something, I would probably like doubt you before I believed you. You know, I'd be like, no, let's take that data again. I can't even believe it. That's so unlikely.
And the outliers are 1.5 standard deviations away, right?
You mean that?
If
there are no outliers for a normal distribution,
right,
but
you find outliers depending 0.7 away from 1.5 standard deviations.
yeah, but 1.5 times it doesn't have to do with the standard deviation. It was 1.5 times the I2R. Remember that? Yeah, you missed that one. Plus Q3 or whatever, or minus that subtracted from Q1. Yeah. So we're starting to like use standard deviations as a measuring rod of how weird you are. So you can see if you're, between -3 and 3 standard deviations, we have basically the whole distribution. And there's the picture broken down by slivers instead of written in that sense. Sometimes people call this the 68, 95, 99.7 rule. I don't know, people report it with different levels of precision, but that's called the empirical rule. Okay? So using the same rule, and I've reproduced the chart down here as well, let's answer this question. I'll give you a second to do it. We're dealing with head circumferences, where we have the mean of this and a standard deviation of this, and we're assuming that it's approximately normal. So use this rule and this picture, if you like, to figure out the answer to these questions. You want to talk about the first one?
So you are adding the standard deviation one time and then subtracting it one time?
Yeah, you noticed those were very convenient values, didn't you?
Yeah.
Yeah.
So then that would be this value.
Yeah, so this was not meant to be rocket science here. You recognize, hopefully, that I've given you the most convenient values ever. And so, yeah, we just get the 68.2% for that first one. We're starting nice and easy here. And then what about, how do we deal with the second one? Do you have a way in on that one, Theo, maybe? No, not yet. Well, think about it again. I think I've given you a convenient value. I'll give you a second to do these. So maybe I need to give you another second to do it at the end. So, have I given you a nice convenient value? okay, so you did 50 plus the other two pieces. You have a question, Alexis? A bonus question for those who are bored by B and C. You have the answer to B? Yes, you could tell. What would that be? Say it louder. What is it? 90 something. It's a lot, right? Where are we, by the way? What's convenient about 25? Yeah, it's exactly 2 standard deviations, right? So we're like here, and we're asking like what percent of the data is below that point, I guess. And so did you come up with it? It looks like most of it is the answer. What is it? 95.4. Now the only small caveat is that we're not just taking these pieces of data between here. I also want that little piece too. So how would we adjust that? But you're in the right zone now. Did you like my part B as well? Think about that. So probably you get a pit circumference of exactly 25. We did more and we did less here. So we're doing on B and C, less and then more. So what does that come out to? Did you adjust it for the tail?
So do you just add like?
Yeah, we need like all of this, I guess is the point, right? Yeah, so what does that come out to be? And there are a number of ways you could add these up. I don't know what the best way is, but so you could do, what is that, 0.1 plus 2.1 plus 13.6 plus 34.1. What do you think the answer to D is? 97?
I got 27.
Yeah, what did you get? I didn't actually calculate this yet. Is it 97 even? Huh? How do you do it? How are you doing? Did you do? You just add them all up? Yeah, right. Did it come out to 97 exactly?
It's 97.7.
97 point. Oh, okay. Yeah, well, how did you do it? I mean, I was suggesting you add all these up. You had a little bit of a faster, what would you say? Oh yeah, that's a good point. Yeah, so you could think, well, the whole thing is 100%. You could just subtract these two. That's a good way to do it. How'd you do it? You had another way too.
I just did 50 and then the ones after because like.
You said this is 50% of the data, so just add on these two. Anyone else have another way? There are a couple nice ways to take advantage of the symmetry of the curve here. Huh? How could you repair, your first guess was 95.4, which is not a bad guess. How could you repair that calculation pretty quickly? You could, huh?
Add 2.1.
Yeah, you could add that piece there too. The other way you could do it is you could say, well, from that you could do 1 minus that and calculate both tails, right? And then divide by 2 or something, right? There are a couple different ways to do it, right? Using the symmetry of the curve and using the fact that the area underneath of it is 100%, right? So, good. And then what's the other piece here? Of course. 2.8. Is that what it is? Isn't it? Or no? 2.3. Sorry. And then this I think this is 0. I think you're right, but we need to like really think about why that would be true. So maybe we'll come back to that. You let that like sink in for a little while. Why it would be like exactly 0.
Wait, how'd you get 0?
Oh, don't worry about me. That was a bonus question. All right. Well, I would like to revisit that, but I also want to make sure you can do your homework. So it's certainly true that we have now a way of thinking about z-scores, about standard deviations, measuring how weird we are in terms of this idea of standard deviations. So on the last example, what if I gave you something that wasn't convenient, like a head size of 23.35? It was really convenient that all the values I gave you were right on the boundaries. But what if I give you this? Where does that fall? How many standard deviations is that above the mean? 22.8, and the standard deviation is 1.1. So how many standard deviations is that? And how did you calculate that, even for the ones you did? Like when we did 25, how how far above the mean was that, and how did you calculate that that was 2 standard deviations? How'd you do it for 25? Yeah, you found like kind of the distance between them, and then you're like, well, if I want to, it's almost like unit conversion. You're like trying to figure out how many standard deviations is that. We'll just divide by the size of the standard deviation. So, I mean, what would that come out to be? Like, how far away is that? How many standard deviations is that? It's like half a standard deviation away, isn't it? And I don't think, the reason I hesitate to show you this formula is because it really just makes sense. I mean, it's just a way of like doing the unit conversion, right? You calculate the distance you are away and then divide by whatever a standard deviation is in our world right now. And that quantifies like the number of standard deviations you have. Notice, of course, that in this particular formulation here, that could come out to be a negative number. Is that a desirable or undesirable property? Is it okay if it comes out to be negative? Yeah, in some sense it's like a distance, so maybe you don't want that to happen. But why could it maybe be desirable? Why would you want to know maybe if it's negative?
Is you above or below the mean?
Yeah, I mean, if I just said like, hey, I scored 3 standard deviations away from the mean in the last test, should you like congratulate me or not? Like, I need to know what the sign of my z-score was. So, let's let's do this one quick. I'm running short on time. Okay, so we've got three tests that have been given for neuroticism, I guess. Okay, and they're each approximately normal tests, but they're different, completely different tests. They have different, like this one you score a 255 on. Is that the person that's most neurotic here? I don't know. But if the mean is 300, then I mean, it's hard to tell here, right? So calculate a z-score for each of them to find out how weird each one is, right? This is the idea of the highest relative score. I don't know if you can give me exact ones or not. Do you have the first one, Franklin? You get the first one. Matt, you want to get the second one? Cassie, you can get the third one. The second one? 1.2. Franklin, did you get the first one yet? 1.7. Cassie, what do you got? Which one? Oh, they're all negative? That's good. I mean, it's good on this test to be negative, isn't it? It's the same thing. So, which has the highest score? We thought maybe it was this one, and actually it is this one, I guess. Right? They're all negative. It's good to score low on this test. Did you get it wrong? Negative 1.5? I just trusted you. That was bad. So who was the high score then? Yeah, actually this guy here, right, is the most neurotic of them. Okay. All right. Well, what if you wanted to actually calculate the percentage of people that you're like more neurotic than, or something like, and we can let our calculator. We can use our calculator to calculate this kind of a probability. So just check your calculator and make sure it works. Okay. Let's see, what should this come out to? What's the probability that your z-score is between -1 and +1? Should come out to be 68.2%, right? So just check your calculator. And on the homework, you're welcome to use this command on your calculator. Normal CDF, it's found just where binomial CDF was as well, on the second bars distribution menu. And for each prob on the homework tonight, I'd like you to also shade a little normal curve to just illustrate to yourself which probability you're calculating, right? And isn't that the region? And did you get for this, when you tried on your calculator, did you get 0.682 approximately?
Yeah.
Good. So it seems like your calculator is working. Good. What should this one be without the calculator? Even without the calculator. Yeah, 0.5. Now how do you do one like this, where we're doing greater than 1.23? How about that? Does that work? Alright, the homework is coming to you. There you go. This is actually homework 3, even though it's so comfortable. You know how we have it. Yours for number 3 of it?
Ready?